This is our final demo for the Computer Science 483 class, Introduction to Robotics. Our final demo was to be able to get an AR drone quadcopter to autonomously follow a given path in the world.
What we're using is a software package called ROS, which stands for the Robot Operating System, for doing our control. And we use OpenCV for vision processing. And the simulator that you see right here is Gazebo. All right, so for searching, the quadcopter will take off in just a sec, and it's going to be traveling straight until it detects any orange, which is done by the vision processing. It's a very simple searching algorithm, but it can be easily extended. So as you can see here, it's taking off, and it's just flying straight until it sees orange.
Yep, so what you see right here is the bottom-facing camera of the quadcopter, and it's identifying an orange line. And for vision processing, what it does is once it's identified the orange line, it negates that image and finds the midpoint of the two gray shoulder areas that you see, so that it can figure out if it's flying straight or not.
After we get the midpoints of the gray spaces, we use those X and Y coordinates to try and keep those points within the bounding box that you can see. That way it can stay somewhat centered over the line and not be off kilter with the line, so it can fly straight.
The quadcopter is designed to follow the line until it detects the end of path marker, which is blue. And you can see here it detected the blue, and then it lands.
So our searching algorithm is pretty simple right now. All we do is once we take off, we just fly straight until we see orange, and then that leads to the tracking state. So if we were to change the searching algorithm, we would do something along the lines of spiraling outwards while gaining altitude. That way you can cover more ground and also increase your visibility as you increase altitude. And then once we identify orange, then we could drop back down to an appropriate altitude for tracking.
And altitude, when we're just tracking the line, is actually a little bit of a problem right now. We don't do any sort of altitude correction, so you can see that the longer the drone flies around, the closer it will get to the line, which means it has a harder time making smaller adjustments. So to improve that, or to offset that kind of problem, what we can do is implement some sort of height control, so that if it drops below a certain threshold, we would just raise the drone's height a little bit.
In addition to that, to help with the small corrections, we could implement some sort of controller, like a PID controller, so that way we can do smaller corrections when it's just a little bit outside the bounding box, and then larger corrections for things like sharp turns.
As you can see here, the drone is much closer to the orange line. That's because over time, every movement that the drone makes causes it to lose a little bit of altitude. So over time, this makes it so that the drone is basically following only a couple of inches away from the line. This causes a lot of serious mistakes because it will cause the drone to overcorrect.